Welcome to today's explainer. At first glance, the science of soil compaction, it sounds a bit dry, right? Pun absolutely intended. But let's completely reframe how we look at the ground beneath our feet. What we're actually exploring today is a high-stakes matchmaking game for building solid foundations. Every skyscraper, every massive highway, and every sturdy bridge depends entirely on finding the perfect structural partner for the specific earth it sits on. If we get this match wrong, total structural failure. But when we get it right, well, that's where the engineering magic literally happens.
Okay, let's just quickly glance at our roadmap for today. We're going to cover the mechanics of compaction, the magic of moisture, cohesive versus granular soils, meet the rollers, matching soil to machine, and finally, getting that perfect surface finish. Let's dive right in.
Section 1. The mechanics of compaction. Building the foundation.
So what's our ultimate enemy on any job site? It's loose, uncompacted earth. Why? Because it's absolutely full of tiny, hidden pockets of air. Basically, compaction is just a mechanical process where we aggressively force those solid soil particles closer together. By doing this, we are fundamentally increasing what engineers call the dry apparent specific weight. But more importantly, we're squeezing out the air to drastically reduce the void ratio and porosity. Shrink those empty spaces and boom, you've dramatically improved both the mechanical strength and the hydraulic properties of the ground. You get a dense, unyielding base that is totally ready to support massive loads.
Moving on to Section 2, the magic of moisture, the ultimate catalyst.
Now, check out this classic compaction curve. It proves that adding water to a site isn't just some guessing game, it's incredibly precise. On the vertical axis, we have our target, maximum dry density, and on the horizontal, moisture content. See how that curve rises, hits a peak, and then just drops off? That visually proves there is a perfect mathematical moisture sweet spot. Hit that exact peak, and your machinery is going to achieve maximum density with the absolute least amount of effort. Miss it, you are in for a seriously uphill battle.
To really understand why that curve peaks, we got to look at what happens on either side of it. On the dry side, before we hit that optimum point, adding water is actually a huge help. It acts like a mechanical lubricant, reducing friction so the particles just slide past each other and pack in nice and tight. But push past that sweet spot into the wet side and disaster strikes. Excess water actually starts absorbing the energy from your heavy machinery. Worse, it prevents the void ratio from dropping and traps air bubbles inside. This creates this dreaded condition called borohachudo, where the soil gets rubbery. So your massive machine rolls over it, the earth compresses, and then just bounces right back. Totally defeats the purpose, right?
Section 3, cohesive versus granular soils, a tale of two behaviors.
Treating all dirt exactly the same is a massive engineering mistake. You've got two completely different personalities here. First, we have fine, cohesive soils. Think clays and silts. Because these particles are microscopically small, their behavior is actually governed by surface electrochemical forces. They bind together into these complex, sticky, flocculated structures, kind of like clumps of loose wool. Then, on the flip side, we have granular soils, like sand and gravel. These are much chunkier. They don't stick together electrically. They just rely purely on gravity and physical friction, resting against one another. So as you can probably guess, breaking down an electrical bond requires a totally different approach than just settling a pile of gravel.
All right, Section 4, meet the rollers, the heavy contenders.
Before we actually look at the specific machines, we really need to understand their weapons. There are 4 unique types of energy, or attacks, we use to conquer loose soil. First up is static energy. That's just pure, crushing downward compression. Next is kneading, which aggressively manipulates the soil to break those complex bonds we just talked about. Third is dynamic energy, using intense vibration to literally shake particles into place. And finally, impact or percussion energy, relying on sudden, heavy blows to force accommodation. Every single roller out there relies on one or a combo of these exact techniques.
So let's see how this energy translates into the real world. Take the classic static, smooth steel roller. Historically, these absolute beasts, often weighing around 7,200 pounds and heavily ballasted with water or sand, were used basically everywhere across all sites. But engineering has evolved. Today, that sheer compressive static energy is highly specialized. Now, we primarily reserve these machines for the initial accommodation of loose dirt, or, really crucially, to get that absolute final, perfectly flat surface finish at the very end of a job.
Which brings us to Section 5, matching soil to machine, the perfect pairings.
Okay, here is your definitive matchmaking chart. Remember those sticky electrochemical bonds in cohesive soils we talked about earlier? Well, to break them, you absolutely need the aggressive kneading action of a sheepfoot roller or a heavy pneumatic tire. Granular soils, on the other hand, respond best to being shaken into place, which means they demand dynamic, vibratory equipment. And what if you're dealing with mixed soil? Well, then you gotta compromise. You'd use a combination machine, like a corrugated vibratory roller, to tackle both the friction of the granular chunks and the stickiness of the clay all at once.
Let's zoom in on granular soils for just a second, because optimizing this specific match requires a very particular setup. You can't just turn on a vibratory roller and call it a day. To build a highly efficient system here, the data shows we must combine a low frequency with a high amplitude vibration. Why? Because that high amplitude gives you enough lifting energy to momentarily overcome the gravity and friction holding those chunky particles in place. Meanwhile, the low frequency ensures those penetrating waves reach incredibly deep, letting the soil perfectly resettle into the tightest possible configuration.
And finally, Section 6, the perfect surface finish, sealing the deal.
Check out the stark visual contrast in the footprints these machines leave behind. Looking at the deeply textured, honestly violently penetrated surface left by a corrugated sheepfoot roller, I mean, it is fantastic for kneading cohesive soil from the bottom up, but there's literally no way you're painting traffic lines on that. That is exactly why we bring in the smooth steel roller to follow up. It provides that final, uniform, perfectly sealed flat finish you absolutely need for a stable working surface.
Because in a real-world field application, you don't just dump a giant mountain of dirt and try to crush it all at once. That just won't work. Soil is meticulously laid out, the moisture is carefully corrected, and it's compacted in uniform, sequential layers, usually averaging just 10 to 30 centimeters thick. That guarantees the machine's energy can actually penetrate all the way to the bottom of the layer. So layer by layer, the right equipment does the heavy lifting, until finally, a static smooth or pneumatic roller comes in to seal the very top layer, giving us that pristine, impermeable finish.
And that brings us to the end of today's explainer. I want to leave you with this final thought. Isn't it just incredible how understanding the microscopic, entirely invisible electrochemical structures of mud directly dictates the engineering of the massive 7,200-pound machinery we select to build our roads? It's all connected. So the next time you're driving smoothly down a newly paved highway, I really hope you think about the high-stakes matchmaking that happened in the earth right beneath your tires. Thanks so much for learning with me today, and keep staying curious.